SwayamPrabha. Digital India. Educated India.
Hello everyone. So we've been talking about the small scales of turbulence, and in the last class we had derived some equations for the Kolmogorov scales, which Kolmogorov had called it the inner scales, and which he derived. So just to refresh your memory, these are the Kolmogorov scales: the Kolmogorov length scale, the Kolmogorov time scale, and the Kolmogorov velocity scale, which he called the micro scales, or he, in fact, in his literature, he called it the inner scales. This was developed in the 1940s. But this is based on one of the fundamental theories of turbulence, which is the fact that starting with the premise that large scales, large length scales have large time scales, and small length scales are associated with small time scales. So Kolmogorov made the argument that if small length scales are associated with small time scales, then as the large length scales are breaking up into small length scales, the time with which the small length scales stay before getting dissipated by viscosity is very short due to the small time scales. In that case, you can say that the rate at which the energy is being supplied from the large scales to the small scales is equal to the energy at which it just gets dissipated. So the rate at which energy gets dissipated at the small scales is only dependent on two quantities: the dissipation rate and the kinematic viscosity. The dissipation rate, because that is the rate at which energy is being dissipated, and the viscosity, because viscosity plays a role in the dissipation of energy at the small scales. So just two quantities: dissipation rate epsilon and the kinematic viscosity nu. It was this basis that Kolmogorov used in order to derive his scales, which he called the inner scales. Now, the way he derived it, he purely just used a dimensional analysis, the Buckingham pi theorem, to come up with these scales. So eta is equal to nu cube over epsilon to the 1/4. Tau, which is the Kolmogorov time scale, is nu over epsilon to the half. And v, which is the Kolmogorov velocity scale, is nu epsilon the whole to the 1/4. These are called now the Kolmogorov microscales in length, time, and velocity respectively. Now, one additional point before we move on to the new topic for this class. Since we are talking about the smaller scales in length, time, and velocity, the Reynolds number associated with these scales has to be very small. If they are very small, how small should they be? So he assumed that let it be the smallest whole number, so 1. So that's also an assumption that he made, that the Reynolds number associated with these scales, since they are very small, let it be 1. Let it be the smallest number, very small, or of the order of 1. So eta v over nu is equal to 1. So with that as the background, let's look at today an implicit estimate for the dissipation rate. So we are going to focus on the dissipation rate here. Now, if you think about it, we derived all this assuming that the rate at which energy is transferred from the large scales to the small scales only depends on the dissipation rate and the viscosity. So you can say the difference between the large scale and small scale is the dissipation rate. Right? So that dissipation rate can be related to the length and velocity scales, because it is the rate at which energy is being transferred from large scales to small scales. So it can be related to the length and velocity scales. And you can assume, say, that the rate at which large eddies supply energy to the small eddies as they are breaking down is proportional to the time scale. That's not a bad assumption. Now, think about the amount of kinetic energy per unit mass. The amount of kinetic energy per unit mass is proportional to U squared per unit mass, right? Half mv squared is the equation for kinetic energy. So we are saying the amount of kinetic energy is proportional to U squared, which means the rate of transfer of energy, if it is proportional to the time scale. The time scale is of the order of magnitude of L over U. So the rate at which the rate of transfer of energy is proportional to U over L, right? The time scale is essentially L over U. So the rate of transfer of energy will be proportional to U over L, in which case the kinetic energy is U squared and the time scale is L over U. So you can say the rate of energy supplied to the small scales is U squared divided by time, which is L over U. U squared divided by time, which is L over U, which is essentially what I've written here. U squared times U over L, which is U cube over L. So this is the rate of energy supplied to the small scales, coming from the large scales, but the rate of the energy supplied to the small scales. This should be the same order of magnitude as the dissipation rate, isn't it? Because small length scales are associated with small time scales. So this is very clearly coupled with our discussion that we had in the last class. Small length scales have small time scales. So the small length scales don't stay for long. As soon as the small length scales are formed, they are dissipated. Large scales break up to small scales, they get dissipated. Large scales break into small scales, they get dissipated because of viscosity. And that dissipation rate is the same rate at which energy is being supplied to the small scales by the large scales. So that dissipation rate, you can say, is of the same order of magnitude as U cube over L. And this is the same rate at which energy is being supplied to the small scales. So in that sense, you can say, just based on this statement, just based on equation 24, you can say that the viscous dissipation, because the dissipation is happening due to viscosity, isn't it? The viscous dissipation can be estimated from the large scale dynamics. Where is the large scale dynamics coming from? This is the large scale dynamics, isn't it? The viscous dissipation can be estimated from the large scale dynamics, and as you can see, this does not involve viscosity. So we started by saying that anything in the small scale should only depend on two quantities. One is the dissipation rate and one is the viscosity, and that makes sense because everything is happening. Basically, the energy transfer, the energy cascade is happening at the rate at which energy is being dissipated at the small scales. And what is the mechanism that causes the energy to get dissipated? It is the viscosity. So they had to be related to two quantities, which is dissipation rate and viscosity. That's what we started with. Then we tried to make the assumption that the dissipation rate can be related to the large scale dynamics, which is how we came up with this equation, which is equation number 24. The dissipation rate is of the order of magnitude of U cube over L. So in this sense, epsilon dissipation is clearly seen as a passive process. It's not determining the process. It proceeds at a rate at which the energy is being supplied, isn't it? Proceeds at a rate that is dependent on the large scale dynamics. And what is the large scale dynamics? What is the primary mechanism for the large scale dynamics? It is the inviscid mechanism. It is the inertial behavior. The inviscid inertial behavior is responsible for the large scale dynamics. That is how we are relating the dissipation rate to the large scale dynamics. So that is what we mean by this particular thing, an inviscid estimate for the dissipation rate. We are saying the dissipation rate depends on the large scale dynamics, which happens due to the inertial behavior of the large scales, U cube over L. So this is now one of the really important assumptions of turbulence theory. It claims that the large eddies lose a significant fraction of their energy, kinetic energy, which is kinetic energy per unit mass. We are always talking per unit mass in this class. So kinetic energy per unit mass, which is half u squared. A significant fraction of their energy is lost in one, what we call a turnover time. It's called an eddy turnover time, which is L over U. So in one L over U, the large scales transfer the energy to the small scales and the small scales dissipate. In the second eddy turnover time, the large scales again transfer the energy to the small scales dissipate. So a significant fraction of the energy of the large eddies is lost in one eddy turnover time. So in that sense, you can define one eddy turnover time as the time taken for the energy, for a huge fraction of the energy of the large eddies to completely get dissipated at the small scales, by the way. So what does this also mean? This also means that the nonlinear mechanism that makes small eddies out of large ones, isn't it? The large scales are what are breaking down into small scales. So the nonlinear mechanism that makes small eddies out of large ones are as dissipative. Even though the dissipation is not happening at the large scales, they are as dissipative as the characteristic time permits. And that characteristic time is this eddy turnover time. I hope that is clear. So again, we talked about the large eddies losing a significant fraction of their energy to the small scales due to the inertial or inviscid behavior, because the inertial behavior is inviscid, right? It has nothing to do with viscosity. It happens due to, say, vortex stretching. It happens due to the nonlinear term, the convective term. But there is no viscous dissipation there, or if it is there, it is very negligible. So that's what we mean by this sentence. The large eddies lose a a negligible fraction of their energy to direct viscous dissipation effects. The viscous dissipation is only predominant at the small scales. It is not dominant at the large scales. So when the large eddies lose of energy to viscous dissipation, it's negligible, almost not there. And that time scale, you can say that is of the order of L squared over nu, because it depends on viscosity, isn't it? Viscous dissipation would depend on viscosity. I'm not talking about the inertial behavior, the loss due to inertial behavior. I'm talking about the loss due to viscous dissipation at the large scales. See, we never said that it does not, viscosity exists everywhere. It exists at the large scales also, except its effect is negligible. So that is clear from this time scale here, which is L squared over nu. And you can say that the viscous energy loss proceeds at a rate that is nu u squared over L squared. So that comes because if this is the time scale, L squared over nu is the time scale, kinetic energy is u squared. So now the time scale is different. Right? The viscous dissipation time scale is different. So if you just have to take u squared divided by L squared over nu. I'm sorry. L squared over nu. So that's how you get nu u squared over L squared. Isn't it? Now the time scale is different. This is the viscous dissipation, the negligible viscous dissipation happening at the large scales. That time scale is L squared over nu, pure dimensional analysis. So kinetic energy is u squared divided by time, just like we did in the previous one, except earlier, due to the inertial behavior, the kinetic energy was still u squared, but the time scale was L over u. Now it is L squared over nu. So now if you compare this, the viscous dissipation at the large scales, it is very small compared to u cube over L, which is the dissipation rate. Because think about it, We are talking about turbulent flow here. For a turbulent flow, the viscosity generally is very small. And if a viscosity is involved in the numerator like you have here, then it's going to be a very small number. So that's what we mean by nu u squared over L squared is very small compared to u cube over L, because viscosity itself is very small. So this nonlinear mechanism is dissipative because it creates smaller and smaller eddies until the eddy size becomes so small that the viscous dissipation of the kinetic energy occurs immediately. And that is sort of illustrated through this a drop of ink in water. How when you put a drop of ink in water, the drop is your largest scale, and you start with a single length scale. Now, because of some disturbance, it spreads, it breaks down into smaller and smaller scales. That is what you're seeing here. One drop of ink creates all these different structures. And as you can see, it is getting stretched and broken down into smaller and smaller scales. Eventually, it dissipates. Now, when the ink dissipates, what you eventually end up seeing is a bluish, if the ink is blue, you end up seeing a colored water there, which means it has dissipated. That's what we mean by that. Until then, you see the ink as such, as a distinct structure. So, with this relationship between dissipation rate and the large scale dynamics, right, where epsilon is proportional to u cube over L. So with that, let's substitute that into the Kolmogorov scale relationship that we had earlier. So the Kolmogorov scale relationship is, what is it? By definition, it is nu cube over epsilon to the 1/4. Now if I substitute epsilon here, what do I get? I get nu cube over u cube times L to the 1/4. So this is eta. If I want to take the ratio of the Kolmogorov scale to the large scale, eta over L, then what I'll need to do is this becomes nu cube over u cube L cube to the 1/4, which is equal to Re to the negative 3/4. That's how I get it. So now just think about this relationship. Eta over L, the ratio of the smallest scale, the Kolmogorov scale, to a large scale estimate, which is L. So eta over L is Re to the negative 3/4. Let me do one more. If I think about what tau is, okay, so tau is by definition, according to Kolmogorov, is nu over epsilon to the half. Now I substitute nu over u cube over L to the half. So then if I take tau by t, like a Kolmogorov timescale to some kind of large timescale, which is obviously t is L over u, so that becomes tau u over L, then this becomes nu L u squared over u cube L squared to the half, isn't it? So tau over t, which is equal to tau u over L, is nu over ul to the half, which is equal to Re to the minus half. So similarly, you can get a relationship for V over U equals Re to the minus 1/4. Now think about this. The smallest length scale to the large length scale is given by Re to the negative 3/4. So as the Reynolds number keeps increasing, your eta compared to the large length scale is keeping on decreasing. The difference, the gap between the smallest length scale and the large length scale keeps increasing as the Reynolds number keeps increasing. Same goes for time scale. We could know this because small length scales are associated with small time scales and large length scales are associated with large time scales. So tau u over L or tau over T is Re to the minus half. So as Reynolds number keeps increasing, the gap between the Kolmogorov timescale and a large timescale estimate keeps increasing. Same goes for the velocity scale. So it just gets to be wider and wider, right? The gap between the small length scale and the large length scale, and the small time scale and the large time scale, and the small velocity scale and the large velocity scale. So the small scales tend to be much smaller as the Reynolds number increases. So that's essentially what this means. The separation in scale widens as the Reynolds number increases. And it gets to be so wide that you could imagine there's going to be a statistical independence of the small scales. What do I mean by that? It almost will not depend on what the large scales look like, because they are so small compared to the large scales that there is a statistical independence there. And then because of that, there is also a dynamic equilibrium state at the very high Reynolds numbers, because they are so small compared to the large scales. And again, when we are talking about turbulent flow, we are just assuming that the Reynolds number is very, very high, which means the separation is already quite large between the small scales and the large scales. If that is the case, we can assume there is a statistical independence with the small scales and the dynamic equilibrium of the small scales as well. So let's see what that means, right? So if you take two turbulent flows with different Reynolds numbers, but the same integral length scale, meaning it's the same large length scale. So two turbulent flows, different Reynolds number, but same large scale. Then the difference between the two turbulent flows will be the size of the smallest eddies, because the Reynolds number is different. That causes eta to be different. So you would think that at a low Reynolds number, you would have a relatively coarse, right? A small scale structure, coarse small scale structure, as opposed to a fine small scale structure. You can see this in this picture here. Any guesses on which one is the lower Reynolds number? Here, these are jets at two different Reynolds numbers. Let's call this RE1 and let's call this RE2. Any guesses on which one is the smaller Reynolds number? Clearly, RE1 is less than RE2, because the lower the Reynolds number, the more coarse your structure is. So as you can see, the small scales here, again, these are two different jets at the same nozzle diameter, which means the large scale is the same in both cases. It is L and it is L. Whereas the small scale is different. It is eta 1 and it is eta 2. That is because eta 2 is less than eta 1, as is clear from the picture. You have a more fine-grained structure, fine-grained small-scale structure, and you have a more coarse-grained small-scale structure. So RE1 is less than RE2, and because of that, eta 2 is less than eta 1. Because as you know, eta over L is of the order of magnitude of Re to the minus 3/4. So as Reynolds number increases, eta keeps on decreasing, and that's what has happened here. So that is clear from the picture, isn't it? The other point that I want to make is related to vorticity. Now, as you know, vorticity has dimensions of per second, right? Because it is a velocity gradient, which means it will have units of per second or frequency. In other words, it will actually be proportional to the order of magnitude of the reciprocal of the time scale, because the units of vorticity is frequency or per second, which means it will be proportional to the reciprocal of the time scale. So that way you can see that if I look at equation number 26, because the time scale of the Kolmogorov scale, the Kolmogorov time scale is much less than the Kolmogorov the Kolmogorov time scale is much less than the large time scale, as is clear from equation 26, because it depends on the Reynolds number to the negative half, isn't it? So Kolmogorov time scale will be much less than the large time scale. So because of that, the vorticity of the small scales is much larger than the large scale motion, because vorticity is proportional to the reciprocal of the time scale. So smaller the time scale, larger the vorticity. Smaller the time scale, larger the vorticity, which means vorticity of the small scale structure is going to be larger than the vorticity of the large scale structure. And that also makes sense because vorticity is velocity gradient. You have more sharp velocity gradients at the small scales compared to the large scales. So that makes sense that vorticity would be larger there at the small scales. And on the other hand, if you look at equation number 27, that indicates that small scale energy is small compared to the large scale energy. V over U is Re to the negative 1/4. So with higher Reynolds number, that V over U is a small number. So small scale energy, V squared over U squared, is also an even smaller number, right? So V squared is much less than U squared. So based on 27, V squared is much less than U squared. So small scale energy is small compared to the large scale energy. And this is typical of all turbulence. So most of the energy is associated with large scale motions and most of the vorticity is associated with small scale motion. So it's important to understand that. Large scales have larger amount of energy and small scales have smaller amount of energy. On the other hand, small scales have higher vorticity and large scales have lower vorticity. So in this class, what we have done is we have actually looked at dissipation and related it to the large scale dynamics. And that is what we meant by an inviscid estimate of that. We did that by relating it to taking the kinetic energy estimate and dividing it by the time scale. So you got U cube over L. Then we derived a set of scale relations using the Kolmogorov equations and substituting the relationship of dissipation rate to large scale dynamics. So epsilon order of magnitude of U cube over L, you substituted that in the Kolmogorov equations of length scale, time scale and velocity scale, and you obtained an estimate for the small scale versus the large scale in terms of the Reynolds number for length, time and velocity. And we realized that as Reynolds number keeps increasing, the gap between small scale and large scale for length, time and velocity, the gap widens, the gap increases. So that is evident from this image, which has looking at two different Reynolds number jets, where one is at lower Reynolds number and the other is at higher Reynolds number, and as the Reynolds number increases, you have a more fine grained structure because the small length scale is keeping on decreasing. I hope this was clear. Thank you.